Good day again, everyone. Welcome to another tutorial by M.I.B. Math is Beautiful. Please remember to like, subscribe, hit the notification bell, keep your comments flowing. Today we'll be looking at sequence and also taking a jab at APs, which are arithmetic progressions, and geometric progressions. Just looking at a whole summary of those two. Now, looking at sequence, the terms in a sequence can be found by their actual position within the sequence. For example, the function an equals n squared, meaning that, for example, the second term, which is a2, can be found by anywhere n is you put 2, and that would be 2 squared is equal to 4. Likewise, if it's the fourth term, that would be denoted by a4, which is actually anywhere n is you put 4, so that would be 4 squared, which is 4 fours, 16. Now, another way to actually look at the terms in the sequence is that they can be found by a relation of or between the terms preceding them. Example, the Fibonacci sequence, right? Now, the Fibonacci sequence, this is denoted by 1, 1, 2, 3, 5, 8, and that would be 13, and this would be 21, so forth, right? Now, this is actually, with the Fibonacci sequence, generally speaking, the first two terms are given, which is 1 and 1, and the subsequent terms are found by adding the two preceding terms. So in this case, the third term, which is 2, is found by adding the second term plus the first term. The fourth term is found by adding the third term plus the second term. Likewise, so in this case, if we're looking at 8, we'll actually get 8 by adding 5 and 3. We'll get 21 by adding 13 and 8. So of course, the term subsequent to 21 would have been, that would be 34, because that would be found by adding 21 and 13. Now, any rule that depends on the values of the previous two terms is called a recurrence relation. So, with respect to the Fibonacci sequence, the rules that govern the Fibonacci sequence is actually indeed a recurrence relation or a recursive formula, depending on which you're accustomed to. Right? Now, the recursive formula that governs the Fibonacci sequence has the formula of, that would be UR, right, which UR denotes a general term, and this would have been equal to UR minus 2 plus UR minus 1. So in this case, we can see that if we were to look at the third term, this would actually be U3, and U3, anywhere R is you put 3, that would be U3 minus 2 plus U3 minus 1, which should actually be simplified to U1 plus U2. As stated before, the third term is found by adding the first term plus the second term. Now, there are two other common types of sequence. One is that those which differ by a common difference D, where the common difference D is denoted by UN minus 1, right? Now, these are called arithmetic progressions. Arithmetic progressions, and they are generally denoted by AP. Now, for example, let us consider this sequence: 3, 6, 9, 12, 15, and so on, right? Now, you realize that 3 is the first term, second term, third, fourth, fifth, respectively. So the common difference in this, just by looking at it, you know that it is 3, 6, 9, 12, 15. The common difference would actually be D equals 3, right? Now, if you were to look at it, you can see that in the case of the formula, if we were to use just a random fourth term, right, this would actually be the fourth term, n equals 4. This would be U4 minus U, n equals 4 4 minus 1. So it's basically u4 minus u3. And 12 minus 9 gives you 3. If we are using 5, this would be 5 minus 4. Fifth term minus the fourth term, which is still 3. If we are using 2, it's the second term minus the first term, which is also 3. So it doesn't matter the order in which you take it, as long as it's the subsequent minus the preceding, then you will always get the same common difference as 3. If by chance you're looking through the sequence and at some point there is a different common difference at some point, then this is not a arithmetic progression, or there may just be some typo with whatever question that was given, right? The second type is one that is that differs by a common ratio, and we call that common ratio R. And this common ratio is generally denoted as un plus 1 divided by un. Now these are called GPs, which are geometric progressions. Right? Good. Now, geometric progressions are geometric sequences. Likewise, arithmetic progressions are arithmetic sequences. So these generally differ by a common ratio. Example, let us consider this sequence: 2, 14, 8, 6. So let's just consider 2, sorry, not 14. 2, 4, 8, 16. Then the next would actually be 32, 64, so on. Right? We can realize that just by looking at it, 2, 4, 8, the common ratio is actually 2. In relation to the formula, if we were to use the second term, then this would actually be u2 plus 1, which is 2 plus 1 is 3. The third term divided by the second term, and 8 divided by 4 is actually 2. If we're actually using the first term, that would be n equal 1, then this would actually be u1 plus 1, which is u2 all over u1, which is 4 divided by 2, still 2. So the common ratio should always be constant. Now, looking back at arithmetic progressions AP, you know that the terms differ by a common difference d, right? So in general, we can actually look at the general notation for AP as written as the first term, which is, as I indicated before, that the first term is always denoted by A, and the second term would be denoted by A plus a common difference of D. So this would actually be A plus D. And the third term would have actually been in relation to the first term A, and the common difference would be A plus 2 times D. So right here we can see 3 is the first term. The third term is 2 times D plus A. So 2 times 3 is 6 plus A, which is 3, would actually give you the 9. And this continues in that pattern or sequence. So this would be 3D and so forth. Right? Now, the nth term of the arithmetic progression, when you look at the sequence, the general sequence of the terms, the nth term would actually be denoted by an equals a plus n minus 1 d. Right? Now, of course, this can be derived from this notation here, but we'll actually get more into that in another tutorial. Now, looking at these two, just to link them, you can see that in the case of the second term, you'll actually get back a plus d, because if n was 2, then this would actually be 2 minus 1, which is 1. So this would, a2 would be indicated by a plus 2 minus 1 d. 2 minus 1 is 1. 1 times d is d. So we can see that both are linked and follows the particular pattern or sequence that was noted. Now, in the case of GP, which differs by a common difference of R, right? The general sequence is defined by the first term, which is a, and then it differs by a common ratio, so it would be a times r, right? Generally r to the 1, and then a times r squared, a times r3 goes down. Now, as you say, this is actually the first term, second term, third term, fourth term going on. Now, note that the common ratio can never be 0, because if the common ratio is 0, then we'll actually have an relatively empty set. Nothing would have been there in terms of a sequence, right? So the nth term of the geometric progression GP, now this can be given by an equals a to the r n minus 1 power, right? Now, looking at this, we can actually relate the two, because we see that for the third term, n equals 3, then this would actually be 3 minus 1, which is 2. So this would be ar squared, right? So these formulas are, these expressions are formulas. All they have done is that they have linked the general sequence of both APs and GPs and get a general formula for the nth term. So we can see that the position of the terms is indeed plays an important part in the overall equation in finding its nth term. Now let us consider these questions here, and it says that we should find the general term of the following: 2, 4, 6, 8, 10. That's for question 1. 2, 4, 8, 16, 32, 64. That's for question 2. And question 3 is 2, negative 4, 8, negative 16, 32. Now, the first thing that we should note is that for AP, remember that the nth term is denoted by an equals a plus n minus 1 times the common difference d. And for GP, the nth term, an, is denoted by ar n minus to the power of n minus 1. So whenever we're doing the question, the first thing to consider is to determine whether or not the sequence is indeed an arithmetic progression AP or a geometric progression GP. Now for question 1, it says that 2, 4, 6, 8, 10. Now looking at this, we can see that this is actually an AP, and the common difference is what the subsequent minus the previous number. So 4 minus 2 is actually 2, 10 minus 8 is 2, 8 minus 6 is 2, likewise. So the common difference is 2, right? So once we have 2, we have 2, which is a common difference. We have the formula that governs the nth term of an AP, and we have the first term, which is a. So therefore, within this formula, we can use these variables to actually write a general formula for the nth term. And this will actually be an equals first term, which is 2, plus n minus 1 times the common difference, which is 2. And this would actually be 2 plus 2n minus 2. And this is indeed 2 minus 2, 2n. So an is equals to 2n. Now if we were to take n is just the position of the term, and put into this formula we should get any of these numbers. For example, 10 is the fifth term. So if we should say 2 times 5, then we should actually indeed get 10. So if we were to look at A3, which is the third term, this is actually 2 times 3, which is equals to 6. So the third term is what? 1, 2, 3, 6. So 2 times 3 is actually 6, and that is good. Now, looking at the second question, we have 2, 4, 8, 16, 32, 64. Now, looking at this sequence, you realize that this differs not by a common difference, but a common ratio. So, right, indeed, it's a geometric progression. And that common ratio is 8 divided by 4, which is 2. 4 divided by 2 is also 2. 64 divided by 32, that is 2. Now the general formula for a GP is denoted by an equals ar raised to the power of n minus 1. So all we need to fill in are the common ratios, the first term, and of course we leave n because n is indicative of the nth term, which governs the general formula. So this would actually be an, first term would actually be 2, common ratio 2 raised to the n minus 1, right? Now, looking at this is the same base, so we can apply the principles of logs that govern same base. This is the same thing as 2 to the 1. So this is actually 2 to the 1 plus n minus 1. So this is raised to 2 to the n, right? And of course, if we should take this formula and look at what was given, they both should match. So in the case of 8 is the third term. So if we take 2 to the third power, then that would be 8. 2 cubes, 8. Now 2 to the fourth power is indeed 16. 2 to the fifth power is indeed 64. Now looking at the third question, 2 minus 4, 8 minus 16, 32. Right? Now we'll see that this is similar to the second question, and the second question was actually, let me put it here, the second question was 2, 4, 8, 16, 32, etc. The only difference is that there's an alternating sign, right, in terms of the polarity between questions 2 and 3. So of course we know that question 3 is actually a GP, but this time the common ratio is negative 2, because minus 4 divided by 2 minus 2 minus 16 divided by 8 minus 2, 32 divided by minus 16, negative 2 as well. Now the general formula that denotes the GP is what? A r raised to the n minus 1. So if we should put in the variables leaving n, if we should put in the knowns, leaving n as the variable, then we will actually have a being the first term times r, which is minus 2, raised to the n minus 1, right? Now a point to note is that whenever you have a sequence that has alternating signs, the first thing that you should consider is in terms of getting the alternating sign, it will always be negative 1 raised to some power, right? That is the first thing that should come to mind whenever you're trying to get the alternating signs. Now this power will be this here, the notation of the power is dependent on whether the negative comes first or it comes second. In our case it comes second, so we'll actually look at how to deal with that situation. Now looking at this, to simplify this, we can simply say this is 2 times negative 1 times 2 raised to the n minus 1. And that is how we get the negative 1 here, right? Good. Now, we have the same basis 2, so this will actually be negative 1 times 2 to the n, because this would be 2 to the 1. 1 minus 1 is 0, leaving n, right? Now, let us check out what this formula is at the moment. If we were to look at A1, which is the first term, then this would be negative 1 times 2 to the 1. But this would actually be 2 to the 1 is 2 times negative 1. This would actually be negative 2. But this is not the case. So in our case here, the first term is actually positive 2. So we'll have to raise this negative 1 to some power to get this as positive. And this will actually indeed be an equals to negative 1 raised to the n plus 1 times 2n. In this case, we can see that when n is actually equals to 1, you get a1 is equals to negative 1 raised to the 2 raised to the 1 plus 1, which is 2 times 2 to the 1. So in the square root of negative 1 is actually 1 times 2. So a1 is equals to 2, right? Likewise, a3 would have been negative 1 raised to the 3 plus 1, which is a squared, right? So this is actually positive, and 2 to the 3 is actually 8. Second one would have been 2 plus 1, which is 3, and then this is actually negative, so that is how you'll actually get the negative 4 here. Now these are actually questions excellently done. Math is beautiful. Thanks for watching this video. Please like, subscribe, hit the notification bell, leave your comments, and visit us on Facebook at M.I.B. Math is Beautiful.